Okay, so think about a force you feel every single second of your life. It's the one keeping you in your chair right now, the one that makes your keys hit the floor when you drop them. Yep, that's gravity. It's so personal and constant, right? But it's also the grand architect of the entire cosmos, sculpting everything from the moon's path around the Earth to the wolts of giant galaxies. So let's dive into this incredible story of discovery. For centuries, this was a real head-scratcher. On one hand, you've got an apple. It falls straight down, picks up speed, and hits the ground. Simple enough. But then you look up and you see the moon, just sailing across the night sky, seemingly forever, in this perfect calm circle. It really feels like they're playing by two completely different rule books. But are they really? To get to the bottom of this, you've got to realize that for a long, long time, people were trying to solve two completely separate, massive mysteries. First, what was this earthly pole that affected everything around us? And second, how could we possibly decode the heavenly dance? The predictable but super complex movements of the planets against the starry background. Forget this. Over 1,500 years, the main idea was Ptolemy's geocentric model. It was simple. Earth is at the center of everything. But to make that model actually match what people saw in the sky, it got messy. It needed planets to move in these things called epicycles, which are basically little circles on top of bigger circles. Then along comes Nicholas Copernicus, who suggests a much cleaner idea, the heliocentric model. He just put the sun in the middle, and boom, all of a sudden, the paths of the planets got a whole lot simpler. Now, the Copernicus model, a huge leap forward for sure, but it wasn't quite perfect. See, when astronomers like Tycho Brahe started making these incredibly precise measurements of the planets, all with the naked eye, by the way, the numbers didn't quite line up with the idea of perfect circles. So, while it was a great idea, it still wasn't the whole story. And the person who finally cracked that cosmic code? That was Johannes Kepler. He took all of Brahe's amazing, lifelong data, and instead of trying to invent a new model, he just looked for the mathematical rules hiding in the numbers. And what he found was just mind-blowing. 3 incredibly simple, elegant laws that perfectly described how the planets were moving. His first law was the real game changer. He proved planets do not move in perfect circles. They move in ellipses. Think of it like a slightly squashed circle. And the sun isn't right in the middle either. It's at one of 2 points inside the ellipse, called foci. This one idea just completely shattered a 2,000-year-old belief in some kind of perfect, heavenly geometry. Okay, so Kepler's second law builds on this. He figured out that if you draw a line from the sun to a planet, that line sweeps out equal amounts of area in equal amounts of time. Now hang on, what does that actually mean for the planet's speed? Well, look at the diagram. For that wide, short area to be the same size as that long, skinny area, the planet has to be moving way faster when it's closer to the sun. It's really that simple. The planet speeds up as it gets closer to the sun, and it slows way down as it moves farther away. It's this beautiful, constant cosmic rhythm. Kepler's third law, this is where it feels like pure magic. He discovered this incredible mathematical link between how long a planet's year is, that's its orbital period, and how far it is from the sun. To be specific, if you take the period t and square it, and then divide that by its average distance, a, cubed, you get the same number for every single planet. I mean, look at that last column. It's basically a constant. It's like a cosmic metronome ticking away across the entire solar system. So Kepler gave us the rulebook. He laid out the how with almost spooky accuracy. But he couldn't answer the biggest question of all. Why? What was this invisible force reaching across millions of miles of empty space, making sure every planet followed these perfect mathematical rules? And that, of course, brings us to Isaac Newton. You know the story about the falling apple, and whether it's totally true or not, the idea behind it is spot on. Newton's real stroke of genius was to wonder, hey, what if the force that pulls this apple to the ground is the exact same force that reaches all the way up to the moon and pulls it into its orbit? And this was his grand, unifying idea. Gravity wasn't some special thing that only the Earth had. No, it was universal. He realized that every single thing in the universe that has mass pulls on every other thing. The sun pulls on the Earth pulls on the moon, and you right now are pulling on the very screen you're looking at. He managed to capture this whole idea in one stunningly simple equation. The force of gravity, F, is related to how massive the two objects are. But the real secret sauce is that little r squared on the bottom. The force doesn't just get weaker with distance, it gets weaker with the square of the distance. So if you double your distance from something, the gravitational pull drops to just 1/4 of what it was. And that capital G, that's the universal gravitational constant. Think of it as the tuning knob for the entire universe that sets exactly how strong gravity is. And it is an incredibly tiny number. That's why you don't feel the gravitational pull of, say, a bus driving by. It took another 100 years before a brilliant scientist named Henry Cavendish finally figured out a way to actually measure this fundamental constant of nature. And just like that, Newton's single law explained, well, pretty much everything. It perfectly described why things fall on Earth, it was able to mathematically prove all 3 of Kepler's laws, and, this is the really wild part, once we knew the value of G, we could use the law to calculate the mass of our own planet for the first time. We could literally weigh the Earth. All right, so with this incredibly powerful law now in our toolkit, what can we actually do with it? Well, let's take a look at how this understanding is the foundation for our entire modern world of space travel, satellites, and, well, our place in the cosmos. One of the first really important ideas is something called escape speed. Think about it. You throw a ball, gravity brings it back down. You throw it harder, it goes higher, but it still comes down. So the question is there a speed you could throw it so fast that it just never comes back? And the answer is yes. That minimum speed you need to completely break free from a planet's gravitational grip is its escape speed. And for our planet Earth, that speed is an absolutely mind-boggling 11.2 kilometers per second. That's over 25,000 miles per hour. It's the speed that rockets for missions like Voyager or the Mars rovers had to hit just to start their long journey into deep space. And here's a really cool consequence of this. Earth's high escape speed means our planet's gravity is strong enough to hold on to our precious atmosphere. The moon, on the other hand, is much smaller, and its escape speed is only 2.3 kilometers per second. That's so low that any gas molecules would have reached that speed and just drifted off into space ages ago. It's literally why the moon has no air. Now, this brings us to another brilliant idea: orbits. Satellites and the International Space Station, they aren't floating up there in zero gravity. That's a huge misconception. In fact, gravity at that altitude is still about 90% as strong as it is down here. The secret to an orbit is that they are in a constant state of freefall. Imagine this: a satellite is moving sideways so incredibly fast that as gravity is pulling it down toward the ground, the Earth's surface is curving away underneath it at the exact same rate. It's this beautiful, perfect balance between moving forward and being pulled down. It is literally always falling, but it never gets any closer to the ground. So what a journey, right? We went from these ancient puzzles about why things fall and how planets move, to Kepler's beautiful rules that describe the patterns in the sky, all the way to Newton's single powerful law that finally gave us the why. It's this one fundamental force that truly shapes our world and the entire universe we live in. Newton's law gave us mastery of the solar system, but we now know gravity's story didn't stop there. It also governs how stars are born, how galaxies get their shapes, and, as Einstein would later show us, how the very fabric of space-time itself can bend and warp. The quest to understand this force is still going on, which leaves us with that same sense of wonder the very first skygazers must have felt. What are we going to discover next?